Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. Now let's just get started on our set of questions for today's session. Okay, so question 1 is a series of different questions, and we have to answer these multiple choice type questions. So the first is, which of the following can be described as a trans, and select all that apply. So is it a linear alkane with 2 groups, a linear alkane with 3 plus groups, a cycloalkane with 2 groups, cycloalkane with 3 plus groups, or an alkene with 2 groups, or an alkene with 3 or more groups? And then the second part of the question asks if we have a weakly basic nucleophile and a secondary haloalkane, we'll generally get blank mechanisms. And then the mechanism will have blank stereochemistry, either predictable or random. And then due to the planar intermediate, the backside attack transition state, frontside attack transition state, or the anti-periplanar transition state. Okay. So for step 1, or for part 1, which of the following can be described as trans? Okay, so let me describe what a transalkene is. This is when 2 groups lie on opposite sides of the double bond. Okay, so I'll have an example down here. So let's say we had a double bonded carbon. And we had a substituent, like a methyl group, on one side, or like another group on the other side. Then the rest just had hydrogen. So this is an example of a transalkene. And if we were to write this in the cis conformation, our hydrogens would be on the same side, and these substituents would be on the opposite ends. So I'd say the answer for 1 is that you need to have an alkene with 2 groups. Okay, so that's part A. Now let's look at part B. If you had a weakly basic nucleophile, so let's write weak base nucleophile, and a secondary haloalkane, will generally get blank mechanisms. So an example of this is an SN2 mechanism or an SN2 reaction. So let's show another example where we have just any weak base and a secondary haloalkane. So that just means that we have halogen on a carbon with two other substituents on it. And in this mechanism, our weak base will attack the carbon from the opposite end and then kick off the bromine, which is our leaving group in this situation. And now we are left with an alcohol group on our carbon chain plus the bromine that has been kicked off. And then I would say that for this mechanism, the mechanism will have predictable geometry. And the reason for that is because bromine acts as a good leaving group compared to our two methyl groups that are on this chain. So if the OH were to attack and a CH3 would leave, the CH3 minus wouldn't be as stable as a bromine minus ion would. And another reason why it is predictable geometry is because the OH will attack from the back to kick off that bromine. So this is due to the backside attack transition state. Okay, so let's see what the junior tutor says. Which of the following can be described as trans? Aside from alkenes, cycloalkanes can also have its substituents in the cis and trans position. For an alkene, there should be at least 2 or 3 groups that are different from one another, while for a cycloalkane, there must be at least 2 groups occupying opposite sides for it to be considered trans. An linear alkane, on the other hand, cannot be considered a trans molecule because of its tetrahedral geometry. Therefore, from the given choices, with only cycloalkane with 2 and 3 or more groups, as well as the alkene with 2 and 3 or more groups, can be considered trans. Okay, so it's a select all that apply question. So let's look up an example where we have a trans cycloalkane just to see what it looks like. Yep, so you can have like a top face cycloalkane that contains the substituents versus a trans cycloalkane as well. Okay, so that's correct. And if we have a weakly basic nucleophile and secondary haloalkane, we'll generally get most likely proceed via SN1 and E2, and the mechanism will have predictable geometry due to the planar intermediate. However, since SN1 and E2 reactions will compete with one another, a mixture of products will be obtained. Okay, so I'd say this solution is still correct. They gave a lot of examples, but I'll still say that for the second one, an SN2 reaction could probably still occur as well. Okay, so question number 2 asks, what are anomers? Anomers are cyclic monosaccharides oh, I'm running out of space like this. And they can also be described as stereoisomers, of cyclic sugars, that differ in configuration. Okay, so let's write down some examples of anomers. So I'm just going to draw a simple sugar. Like so. And the name of this sugar is alpha D glucopyranose. And for anomers, we can also label the anomeric carbon as well, which is the carbon that is connected to the oxygen and another OH. So it's also known as carbon 1 if we were to label all the carbons in this cyclic sugar as 1, 2, 3, 4, 5, and 6. Okay, so that's one configuration. And we can also draw it in a different configuration. where we can have a different orientation of our alcohol group. So now, instead of the alcohol on carbon 1 pointing down, it can be pointed up. And then I'll just draw the rest in the same configuration. And again, we can label our anomeric carbon. And the name of this anomer is beta, the glucopyranose. Okay, so now let's see what the junior tutor said. There are isomeric forms of cyclic monosaccharide molecules with a difference in configuration at one carbon atom, and the carbon center that differs in the configuration in anomers is called the anomeric carbon. Anomers are mainly found in the monosaccharides with 5 and 6 membered rings called pentose and hexose, because they can form stable heterocyclic structures. Anomers are designated as alpha and beta configurations. Alpha anomer has the oxygen atom at the anomeric carbon is on the same side as that of the reference molecule in a Fischer projection. The beta anomer has the oxygen atom at the anomeric carbon is on the opposite side of the reference molecule in a Fischer projection. Okay, so they have the different anomers of D-glucopyranose, which is the one that I drew. And they also have D-fructofuranose. And they just have the examples below. Alpha anomer has a hydroxyl group present below the ring, and in the beta anomer, the hydroxyl group is present above the ring at the anomeric carbon. The alpha anomer is converted to beta anomer in aqueous solution by a process called mutarotation. So there are different factors that affect the stability of anomers. The hydrogen bonding between one anomeric group and the other groups in the molecule that stabilizes the anomer. You could have repulsion between one anomeric group and the other groups destabilizes the molecule. And finally, group repulsion at axial position C1 and C3 destabilize the anomer. Yep, so this solution is correct. Okay, so question 3 says to explain why chloric acid, which is HClO3, is a stronger acid than chlorous acid, HClO2. Is it because A, the chlorate ion contains more oxygen atoms than the chlorite ion? B, because the oxidation state of chlorine is higher in the chlorate ion than it is in the chlorite ion? Or C, because the chlorate ion ClO3 is a stronger base than the chlorite ion? Okay, so the answer to this is that the chlorous acid, or the chloric acid, which is HClO3, because there are more oxygen atoms in the chlorate ion versus the chlorite ion. Okay, so I'm going to show what happens when we have chloric acid and it dissociates to H plus chlorate. And then I'll just label it. And then let's compare it to the chlorous acid dissociating into its ions H plus and the chlorite. So if we look at our chlorate ion, you'll notice that since it has that extra oxygen, we are able to form more resonance structures with the chlorate ion than we are with the chlorite ion. So therefore, this ion is more stable, and when we have a more stable conjugate base, then that makes our acid more acidic. So that means that our chloric acid is more willing to donate one of its protons, well, its only proton, because the chlorate ion is more stable compared to the chlorite. And there's also an increase in oxidation state. Since when we have an increase in oxygen, in an oxy acid, this increases oxidation state. So therefore, A and B are correct. Okay, so the junior tutor said that because the chlorate ion contains more oxygen atoms than the chlorite, and because the oxidation state of chlorine is higher in chlorate ion than it is in chlorite, A and B are correct, and that is why chloric acid is stronger. Yep, so this solution is correct. And then I'll just add that the chlorate ion is able to form more resonance structures due to its extra oxygen. Therefore, its ion, which is the chlorate, is more stable compared to the fluorite ion. I already mentioned that it was the chloride. I'll just say therefore it is more stable. Okay, so this solution is correct. Okay, so question number 4. Circle the strongest acid and why. So they have a variety of different acids, and they also include the Ka values. So let's recall the definition of Ka. Ka is the acid dissociation constant. And basically, it measures an acid's strength and how well it is able to donate a proton. So when we have a higher Ka value, this means we have a stronger acid. So if we look at our different Ka values, the chlorous acid, HClO2, is 1.1 times 10 to the negative 2. HNO2 is 4.6 times 10 to the negative 4. The hydrogen cyanide, 4.9 times 10 to the negative 10. And finally, the HClO is 2.9 times 10 to the negative 8. So out of all of these values, the chlorous acid contains the highest Ka value. So therefore, HClO2 is the strongest acid. Then I'll just put in brackets that it has the highest Ka value. Okay, so now for part B, of the following acids, which is the stronger? Explain your reasoning, HClO or HClO2. So we already know that HClO2 is stronger because it has its high Ka value. But the reason that it is stronger is because it contains an extra oxygen and has extra oxygen. Okay, so for example, if we were to write the dissociation of these two acids into their respective ions, so we have the chloride ion, the chloride ion is able to form more resonance structures due to its extra oxygen group. So this makes the ion more stable. And when you have a more stable conjugate base, this means that you have a stronger acid, since the acid is more likely to dissociate into those ions and it can donate that proton. Okay, so the junior tutor said that the acid dissociation constant Ka is a quantitative measure of an acid strength in a solution. The higher the Ka value, the stronger the acid will be. From the given groups, the chlorous acid has the highest Ka value, which makes it the strongest acid in the group. Okay, so they also just compared Ka values for part B, but I'm just going to add what I wrote about the extra oxygen as well. So this solution is correct. Okay, so I said that for part B, another reason why HClO2 is stronger is because it has an extra oxygen atom. When it dissociates into H plus and the chlorate ion ClO2 minus, more resonance structures are able to form compared to ClO minus. When we have a more stable conjugate base, we have a stronger acid. Okay, so question number 5 is to write the full electron configuration for chlorine and chlorine minus. So when we write down the electron configuration, it helps when we follow a set of different steps. So the first step is to divide your periodic table into the different orbitals S, P, D, and F. So let's look up what that will look like. So you kind of get something that looks like this. And you can see the first two columns is the S block in the light blue. And this green section is called the P block. And then the middle transition metals is the D block. And then finally, the bottom two rows, the lactanides and actinides, is the F block. So for step 2, starting at hydrogen, we move left to right across the periodic table until we get to our desired element. So in this case, it's chlorine. And then we would write the row number followed by the block letter. And then you write the number of electrons in that orbital shown in the superscript. And then one more thing I'd like to add is that when you get to the D block, you write the row number -1. And when you get to the F block, you write the row number -2. Okay, so after a lot of practice, it kind of gets pretty tedious when you write electron configurations. So first we're going to write the full electron configuration for chlorine. So again, let's find chlorine on this periodic table with all the different sections labeled out. So you can see chlorine is found here, atomic number 17. And then starting from hydrogen, we're going to move left to right across the periodic table, writing the row number, which is 1, followed by the block letter, which is S, and then the number of electrons that are in the 1s orbital. So in this case, s orbitals can hold 2 electrons, and this shows the electron configuration of helium now. And then let's go to the next row. We have 2s and then 2. And then when we get to the p block, the p orbital can house 6 electrons. So we will write 2p6. And this only brings us to the neon. So we have to move to the next row, 3s2. And then we get to the p3p orbital. And then just count out how many electrons until we get to the chlorine. So 1, 2, 3, 4, 5. So we write 3p5. So this is the electron configuration for a ground state chlorine atom. And if we wanted to write the shorthand configuration, we would find the noble gas that comes before chlorine. So in this case, it's neon. And then we'd write neon in square brackets. And then just continue on writing the electron configuration as is. So you write neon and then 3s2, 3p5. So the shorthand configuration is helpful when you need to write the electron configuration of an element, like closer to the bottom of the periodic table, like mercury and platinum. Like you don't want to just write all of the different numbers and letters. You can just write the noble gas that comes before it, and then just continue on with the rest of the electron configuration. So now we need to write the electron configuration of the chlorine ion. So chlorine minus. So chlorine minus has an extra electron, and we know that because it has a -1 charge. So since it has an extra electron, this is going to change our electron configuration. So we're going to add an additional electron. So the first part is the same, 1s2, 2s2, 2p6, 3s2. And then once we get to 3p, it's now going to be 3p6. And if we were to write the shorthand configuration, this would be the same electron configuration as argon. So now we just write argon in square brackets, and these are the two electron configurations. So the junior tutor said that a neutral chlorine atom has 17 electrons, and following the mnemonics, the configuration for chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. So Cl- must have one more electron than the neutral chlorine, so this makes it have 18. So this is isoelectronic with argon, with the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6. Okay, so isoelectronic means that they have the same electron configuration. So this solution is correct. Okay, so question 6 says to define a Bronsted-Lowry base. Okay, so acids and bases can be characterized in different ways. You can have Bronsted-Lowry or Arrhenius acids and bases. But for the Bronsted-Lowry theory, a Bronsted-Lowry base is when you have a proton acceptor, or H+. And on the other hand, when you have a Bronsted-Lowry acid, this is a proton or H+ donor. So let's write out an example where we have NH3 plus water forms the ammonium ion plus OH minus. So if we look at our reaction, we'll see that the NH3 accepts a proton from the water. So this makes our NH3 the Bronsted-Lowry base, and this makes our water the Bronsted-Lowry acid. Since the water is the one that donated one of its protons to the NH3. So now when we have NH4+, this is called the conjugate acid. And when we have the OH-, this is the conjugate base. So the reason why we define these as another acid and another base is because in the reverse reaction, then the NH4 plus, the ammonium ion, is the one that donates one of its protons to the OH minus, which accepts its proton. So they kind of just reverse the roles. So let's see what the junior tutor said. The Bronsted-Lowry acid is an acid-base theory, which states that the base is the proton acceptor and the acid is the proton donor. Okay, so this solution is correct. Okay, so question number 7 is to write the Lewis structures of bromine trifluoride, chlorine pentafluoride, and iodine Epta. Identify those in which the octet rule is not obeyed. Okay, so let's start off with the bromine tetrafluoride. And when we write out the Lewis structures, we want to first find out the total number of valence electrons in the structure. So in the case of bromine, there are 7 valence electrons. And for fluorine, there are also 7 valence electrons. And since we have 3 fluorine atoms, we multiply that by 3. And when we add this together, we get a total of 28 valence electrons. So now when we write out the Lewis structure, we'll have bromine as our central atom. And then I'm just going to draw single bonds to all of the fluorine atoms. And I can also show all of the lone pairs on the fluorine atoms as well. So now if we count out how many electrons I've drawn so far, each bond contains 2 bonding electrons, and we have 3 bonds, and then each fluorine contains 6 electrons in the form of lone pairs. So I only have 24 out of the 28 electrons drawn in this structure. So I'm just going to put the remaining 4 on my central bromine atom, since I'm not able to form double bonds. Okay, so this is our final Lewis structure, and we can see that it does not obey the octet rule. So let me just put at the top here that the bromine can have an expanded valence shell. And it typically occurs when we have electronegative terminal atoms, such as the fluorine. So let's move on to the next example, where we have chlorine pentafluoride. So if we were to calculate the total valence electrons, chlorine has 7, and fluorine also has 7, but there are 5. So when we add these values up, we get a total of 42 electrons. So now let's show chlorine as our central atom. And then I'll draw in 5 single bonds to fluorine. And I'll draw in the lone pairs. So if I count out how many electrons I've drawn so far, I only have 40 out of the 42. So I'm just going to put an extra 2 electrons on the central fluorine atom. So now you can see that for this example, the chlorine also does not follow the octet rule. For the same reason, it's able to expand its valence shell. And then for our third compound, we have iodine, Epta fluoride. So let's calculate the total valence electrons. Iodine contains 7. And fluorine also contains 7. And we have 7 atoms. So adding these all up, we get a total of 56 valence electrons. So again, we're going to show iodine as our central atom. And then just draw out 7 single bonds to fluorine. So already we can see that the iodine also does not follow the octet rule. So now let's draw in all of the lone pairs. Okay, so now if I count out all the electrons in this structure, we'll see that we already have our 56, so we don't need to draw any more lone pairs on the iodine. So these are the 3 Lewis structures. So let's see what the junior tutor said. Is to step 1, list the elements, their valence electrons, and determine the total valence electrons. If the charge is present, add the value of the charge to the total valence electrons when it's negative, or subtract if it's positive. So for all our examples, they didn't contain any charges, so we didn't need to do that step. They got 28 for the first compound and had the same Lewis structure that does not follow the octet rule. For the second structure, they had 42 valence electrons and the extra lone pair on the chlorine. And for the last structure, we just have iodine with the 7 bonds to fluorine, and that follows our rule. Well, it already contains all the electrons that we need, and it also does not follow the octet rule. So this solution is correct. Okay, so question number 8 says to draw a Lewis structure for nitric acid, HNO3, and they told us that the nitrogen atom is in the center and the hydrogen atom is bonded to an oxygen atom. Okay, so that's helpful. And we first need to find out the total valence electrons for nitric acid. So hydrogen contains 1 valence electron, nitrogen has 5, oxygen has 6, and we have 3 oxygen atoms, so we multiply this by 3. And when we add the values all up, we end up getting 24 valence electrons. So the question already gave us a helpful hint that the nitrogen atom is in the center. And let's draw 3 single bonds to all of the oxygens, with one of the oxygens having the bond to the hydrogen. So now if we look at the nitrogen, we need to draw a double bond to one of the oxygens. And then we will fill in all of the lone pairs. Okay, so now we have the final structure for nitric acid, but we also need to include any charges that this Lewis structure might have. So to calculate formal charge, it's going to be the number of valence electrons minus the number of non-bonding electrons minus the number of bonding electrons divided by 2. So let's calculate the formal charge of the single bonded oxygen. There are 6 valence electrons. The number of non-bonding electrons, so the lone pairs, is equal to 6. And there's a single bond containing 2 bonding electrons. So we have 2 divided by 2, making that oxygen have a -1 formal charge. So we can just add a negative beside it. So now let's calculate the formal charge of the double bonded oxygen. It also has 6 valence electrons. This time there are 4 non-bonding electrons and also 4 bonding electrons since there's a double bond. And it has a formal charge of 0. So now if we were to calculate the oxygen with the hydrogen, so I just put OH. There's also 6 valence electrons, 4 non-bonding electrons, and the 2 bonds to it. So like the double bonded oxygen, it also has a formal charge of 0. And if I were to do the same thing for the hydrogen, which has 1 valence electron, no non-bonding electrons, and 2/2 bonded electrons, it's also 0. And finally, let's calculate the formal charge of nitrogen. Nitrogen has 5 valence electrons. There are 0 lone pairs in this structure on nitrogen. And there are 4 bonds to the nitrogen, so that means we have 8 bonding electrons divided by 2. So 5 minus 0 minus 4 is +1. So we know that the nitrogen will contain the positive charge. And typically we want the more electronegative atom to contain the negative charge. So in this case, it's the oxygen. And the nitrogen is able to neutralize that charge as well to get our neutral compound. So the junior tutor said first we need to find the total number of valence electrons, which they got was 24. And then they drew the Lewis structure of the compound. So it doesn't look like the picture showed up. 2 single bond and 1 double bond to nitrogen. Double bond oxygen to nitrogen, or 1 single bond hydrogen is attached to an oxygen. So they just kind of try to describe it. So the steps are correct. The image, however, is not shown. So I'm just going to say the solution is incorrect so that we can look at this. And for the last question, how many valence electrons does chlorine have? So if we recall the atomic number of chlorine, it has an atomic number of 17. So this means it has 17 protons. And if we have a neutral chlorine atom, this means we also have 17 electrons. So if we were to draw out the atom of chlorine and show all of the electrons, the inner shell would contain 2, and then the next shell can hold 8. And the valence shell, so since we already drew out 10 out of the 17, it's going to contain 7. So therefore, chlorine has 7 valence electrons. And it's also in group 17 on the periodic table. And all of the elements in group 17 contain 7 valence electrons as well. So that's another way we can find it out. So the junior tutor drew out the electron configuration. Valence electrons reside in the highest principal quantum number. In this case, it's number 3. And at that energy level, there are 7 electrons available for bonding. Okay, so this solution is correct. So those are all the questions for this session, and if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description. And also, if you enjoyed today's video, you can give it a like and a comment, or you can share with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.